Okay. No, unfortunately. That whole discussion. I can truncate it. I can fix it so the video only shows up to that point where you appeared on the screen, because I didn't turn the thing on. Okay. So there'll be two videos here. I'm not sure where the other one started, but I think I was talking about the fact, okay, first of all, each of these distances is a quarter wavelength. That should be clear. That's how you marked your graphs, and everybody did the graphs right. After we got waves moving in the right direction. Okay. Then, well, you're going to be able to see it. We marked off the half wavelengths here. Okay. It's 2 quarter wavelengths makes a half wavelength. Of course, we could have marked off wavelengths here, here, and here. So we've got 3 wavelengths in this whole picture, right? Okay. What's 2 wavelengths? Well, here's a wavelength. Here's a wavelength. There's 2 wavelengths. There's 3 wavelengths. Okay. Any place we can go from a node to node allows us to model a mode of vibration. Now we want to model the mode, the second mode, where the thing is like this. One end's going up, while the other's going down. You got a node in the middle. If you want to model that, well, you take this section of the wave here, compare it here. Flat, then it's up, down like this. Then it's flat here, and then it's down up like this. If you trace this in time, you can see the second harmonic. If you can't see that in terms of what you did with the chain, grab a chain, make a second harmonic until you see it. Okay. There it is. Okay. Now, the third harmonic. Well, what do you have? You have a node at this end, a node at that end. What do you have in the middle? Let's talk about it. Camera off. Okay, so look at what we discussed. Node antinode distance, any node antinode distance here can model your fundamental mode. It's hard to read. Okay. If you want to model your second harmonic, real good place to label this, but I'll do one down here. I'll just write second for the second harmonic. I don't have room. Okay. If you want to do the third harmonic, and I didn't complete these. Fundamental node is node and antinode node. It does end with node. Okay, second harmonic. You got 2 antinodes. Nodes on the end, and you got to have a node between the antinodes. There's your configuration. Here's your configuration for third harmonic. 1, 2, 3 antinodes. Okay, 1, 2, 3 node antinode distances. So that It's hard to read, but that's third harmonic. All right, well. Need to understand that from the picture. And of course. The length of the chain is what it is, right? So for the first harmonic. This distance is your 4.6 meters. Okay. For the second harmonic, it's this distance at 4.6 meters. For the third harmonic, it's this distance, it's 6 meters. So the chain doesn't get longer, it's just that your model has different meanings, meaning that your wavelength is shorter for a third harmonic than it is for a first harmonic. Okay, because your wavelength, I mean, your chain length is just equal to node antinode node distance. Okay, well, let's do this. Okay, so here you got your chain, and this is what it looks like for a real fixed chain. Here's your length L. There's your distribution of nodes and anions for the fundamental. Okay. For the first harmonic, now your nodes and antinodes have to be equally spaced. It's going to put an antinode in the middle. Actually, sir, I get your. The first, okay, we call this the first overtone of the second harmonic. Okay, the third harmonic. Like this. Fourth harmonic. Oh. All right, right. Okay, here. L is 1/2 that because that's a quarter wavelength and that's a quarter of a wavelength. I'll make that even more explicit. It's 2 quarter wavelength. Well, there are your lambdas. Okay. For the nth harmonic, what would it be? Fill it in. Okay, that's very good. Everybody saw the pattern. L is going to be n times 2 lambda over 4, we really write that 2n lambda over 4. But people wrote n times 2 lambda over 4, because it's only 2 lambda over 4, right? Okay. Which is just n lambda over 2. Okay. So once you got this, you need to do the simple algebra, get this, and then you can solve for lambda. You're going to have lambda equal 2L over m. That can go on, but you better not have lambda using a chain less than the length of a couple of links. Okay. You can't get it. A link is going to deform into an antinode, right? You have to have at least 4 or 5 links before you get some reasonable antinode. You'd better have the right local tube and stuff like that. Okay. But that's it. Okay, so now better use F sub n for the frequency of the nth vibration. So frequency is the nth harmonic. Okay, now we go. I went ahead and put subscripts in these lambdas, lambda 1, lambda 2, lambda 3, lambda 4, lambda n. So it's pretty simple. The fundamental of the nth frequency is C over lambda n. And you've got an image that goes with that. Lambda n is how far it is between peaks. And C tells you how far you go in every second. So how many peaks are there in 1 second worth of wave? That's the image. You want to have that in. You want to maybe go back and look at those and really nail these things, okay? Sequence of relationships, because they're all very intuitive. So that's C over L over n. And I can write that as n times C over 2L. I would never attempt to memorize these formulas unless you got a really clear memory. You can reason them out so easily. Okay. That's one way you could express a formula. You could do it n over 2 times C over L. Okay. Whatever rearrangement makes it clearest to you. But the thing that has to be clear is this whole thing. If it is, then you don't need to memorize formulas. You can always reason it out. Because the formulas end up being really simple. Okay. Once you've got the picture. Okay, well, I'm going to show you one of my favorite things in the universe. Turn my hearing aid down a little bit. There, that'll be tolerable. You have my sympathy. Okay. There's the middle of this thing. If a sound wave travels along this thing, the ends are free. So the ends are antinodes. So you have an antinode here, a node here, and an antinode there. Now, close the doors. I don't think there's a tornado. Or dinner. Feel the vibrations. Okay. So what's happening is this end is doing this. There's a node. That end is doing this. This end is down and that end is up. And I know, node. Okay? Like this. As my shoulder goes. Okay. I wasn't sure I'd be able to make it. Just want to make sure I didn't hit my camera. Okay. What's going on there? Different frequency, right? Oscillations are a lot faster. Well, that's because we're doing a longitudinal wave. Transverse wave, the motion of the particles is perpendicular to the motion of propagation, to the direction of propagation. For this one, it's parallel to the direction of propagation. Now, I'm not sure that all that put up on the camera. Make sure when I hit it like this. Well, if I don't tap it out, fingers. Okay. The ends are kind of doing this. One down, one's up, and there's a node in the middle because I'm holding it, it can't move in the middle. Any motion gets damped out very quickly. I can feel it vibrating. I can feel myself pulling the energy from this system. And boy, do I feel energized now. Actually, there was no net gain in energy because I had to put the energy into it, right? And I got a lot less energy out of it here than I put into it by lifting this thing, which exhausted me. Okay, well, anyhow, there it is. Now, if I take this thing and wrap it on the floor, we get this. Okay. So there it is. And I did it roll around my head, but so, okay. That's kind of interesting. Even more interesting. We can balance this on a domino and just tap the end with anything metallic. Get the same thing to happen. Okay. Better, we go to where we figure, okay, antinode, node, antinode, node, antinode. Well, now our harmonics go from antinode to antinode. We have one from here to here. That's what we just observed, an antinode with a node in the middle and an antinode. We want another one, we could go from antinode to antinode. Okay, and you can trace what the picture looks like, you know how to draw it now. And we see that the nodes would have to go a quarter of the way. All I need is a meter slip and a couple of dominoes. Do this. Now these dominoes are kind of thick, they'll dampen out quicker than thin dominoes would. I'm just going to see. Okay. Same thing I was doing with my finger. Nothing new. Now, from here to here is about 76 centimeters. If I go to 38 centimeters, I think I'm going to mark that. If I got one there, I probably have one over here that looks like it, but let's make sure. Yeah. Mark there. Mark here if it doesn't fire off. See what you hear now. Much higher pitch, right? Okay. That damped out pretty quickly because those things are perfectly positioned. So that, you know, there is some vibration going on in contact with this thing and that. Okay. I go to higher harmonics. I got one here. I didn't know this one was marked, but it's something it was. It doesn't take long before I get the harmonics that I can hear. If I lost Hodge harmonic. Let's see what I've got. Okay. So here's thing going up harmonic. And you can go on with even higher harmonic. I can hear that one. Well, for that, if you take Audacity and pick up that sound and look at the distance between the peaks, you're going to get a nice sound wave. You figure out how fast sound travels in Lulu. I mean, you know what the wavelength is. Yeah. Right there's a node antinode distance, so there's your wavelength. Okay, that's got 3 antinodes. That's, yeah, what we did, we should do is go from here, here. 1, 2, 3. Actually, this one would have been 3 antinodes. Let's use this model. We got a measurement of sound in aluminum. I've got this thing here, which is steel. Doesn't work as well. Okay. So if we pick up that frequency on Audacity, know what the length of this thing is. We can corroborate what all the tables tell us about the speed of sound in steel. And with this one, we can do it as well. This is also aluminum, so we're not going to get anything new. We're just going to see if we're consistent. I don't quite have it right. Well, that's a transfer vibration. Okay. Which allows you to determine what the material property is and how it responds to the pedal. Okay. Anyhow, there we have it. Now,